Thank you very much for having me as your speaker this morning. For me, mornings always start a little bit too early. I don't like them very much, so I'm more a guy for the afternoon, particularly on the Saturday, so thank you. I bring you some pictures. I try not to be boring you with what I have to say. I'll guide you a little bit through what is software in satellite systems. It goes a bit through my experience. I will put the missions more or less in the order I came across them. The first one I have to you is something that looks like a house, a roof that has been ripped off by a tornado or so. It is called Cryosat, and it was a very interesting mission. It was my first mission in space. Back then I didn't know anything about space. And this mission had something particularly interesting, but a little bit upsetting at a certain point. It was that when the satellite was launched, the rocket failed over. So the rocket just it was quite curious because the rocket was a modified version of SS-19. You may realize that the SS-19 it was an ICBM from the Soviet Union meant to deliver nuclear warheads to the United States. So the rocket did what he was trained to do, but it fell off in the Arctic. We eventually did another one, which was called Cryosat 2, and that one went okay and is still on orbit. What was here, the first time I went to this, when I went to this mission was the first time I went to get in contact with a language called Ada. Probably you don't know what Ada is, or probably you do, I don't know. For those who do not know the Ada programming language, I can tell you it's some kind of programming language that makes your software do not compile for weeks on a row because you are struggling with the types. Once you understand what the type is, then your code starts to compile at a certain point. But before it does not compile at all because if you do not have your types right, it will just fail over and over again. So Ada is what is strong typing all about. It is really strong typing. It's not just they have ints and shorts. No, it is far more than that. For you to have an idea what kind of processors you can, or computers you can find on board the spacecraft, here on Cryosat we had something quite not so performant to these days standards. It was a 20 megahertz Spark V7 CPU with 2 megabytes of RAM. That was the central computer. There was the spacecraft has not only one computer, it has a central computer, and then has other computers that control the different equipments. They are connected through data links or data buses. There's a data bus which is very common there. It's called Melbus, or 1553B is a data bus that has been delivered, engineered initially for the F-16 fighter. So it was not a very big computer, as you see. So ERC32 was the name. 20 megahertz Spark V7 implementation with 2 megabytes of static RAM. And the software boots from a PROM memory, a small boot software there. There was no operating system in this particular case, so there was just a very simple cyclic scheduler implemented on top of 2 clock interrupts, one at 1 hertz and one at 10 hertz. So at each 100 milliseconds, a collection of so-called tasks. They were not really tasks, just a collection of function pointers in a table. The software just goes there and executes those function pointers. This was the software of the main computer, the one that does the interface with the ground. Then there were several other systems. What you see in front of it, these cones here. This was the payload. This is the payload. It's a radar altimeter. A synthetic interferometer radar altimeter is called Cyril. The purpose of Cryosat was to measure the thickness of ice and the variation of the thickness of ice on Earth. And the urgency of sending the satellite up there was that if we would send it much later, there might be no further ice to measure, and that would be a huge loss of investment to have a satellite to measure ice that is no longer there. So you can check on the ESA website for these and other missions. Cryosat is a polar system, which is quite common in Earth observation. So polar systems are satellites that are in low Earth orbit, or as we say, LEO, and they go from pole to pole with a given inclination. And when they are solar synchronous, which is a subtype of solar orbiter, what happens is, you see here in the patch, they as the satellite goes around the Earth keeps rotating. Of course, it continues rotating all the day and night, even when we sleep. And what happens is that, for instance, the satellite always passes over the same spot on Earth at the same solar time. So the satellite will be taking pictures at Porto always at the same solar time, which of course is quite important if your satellite is an optical satellite. Even if it is radar, the illumination of the sun may change the reflection conditions of the objects being observed. So the solar synchronous mission type is quite common, and is the kind of mission that gives you globes. It keeps taking patches and patches and patches, and a single satellite can give a globe depends on the swatch, if it is narrower or larger, but about, let's say, a week. If you have a single satellite, you can have a full globe in a week. If you have multiple satellites, one after the other, if you have two in opposite points in 180 degrees from each other, then of course you can have a globe in half a week. So if you put more satellites into, you can have globes even faster. So if you have many satellites, you can have new globes every single day. So Cryosat was one of these. So it's very common to have this type of orbit in Earth observation satellites. Here, there was another mission. I don't know whether it was started before or after, because I was not in the original team. And this was a mission which was actually a twin mission. And our work here was a bit different. So here we also worked on the main computer, but this time we have done the first thing we have done here was the qualification of the real-time operating system used by the center computer. We used something called RTEMS. Some might know, some might not. RTEMS is an open source implementation of a real-time operating system. You can get it from the internet. It was originally developed by United States Army as a modernization program for missile systems. But then it went online. It went open source, and it's used in many space embedded systems. So our purpose here, there was already the operating system. So there's a real-time operating system with the features you expect an operating system to have. You have tasks, you have semaphores, you have all those things. Of course, you don't have a GUI because you don't need it on a satellite. Our purpose is to tailor it out because it contains a lot of packages. So remove everything that is not strictly required for the mission, and then do the testing until you get the required coverage according to the qualification standard that applies. So remove off all the unwanted features or all the not used features. Do the testing, do the reverse engineering, and because the open source version keeps going online and some people keep posting bugs there, we're also supposed to keep things into synchronization. At a certain point, it's quite a challenge, but it's a nice challenge because we are doing some adaptations and some modifications. At a certain point, it's quite difficult to match your code to the original code because people may be just when they are posting bugs online, they are posting bugs with respect to the original code. But meanwhile, you may have already changed the code, so you need to take a little bit more care to see whether that still applies to you or how does that apply to you, because the adaptation meant to change it a bit. These two satellites were very interesting satellites. So what you see in front, the big one, is called Herschel. Both of them are decommissioned now because they were cryogenic bodies and the coolant went away already. So Herschel is a far infrared space telescope. So the purpose of far infrared space telescopes is to observe objects that are either very distant or very faint. And infrared telescopes are only feasible in space because if you cannot observe infrared here. So for you to have an idea, the main detector was cooled down to 0.9 Kelvin, which is pretty cold. It's very, very, very pretty. Supposedly at 0 Kelvin, electrons stop to move. So 0.9 Kelvin is quite cold. The other one on the back is called Planck. So the mission was a twin mission called Herschel Planck. Planck is a continuation of a satellite that existed there before, which was called WMAP. And Planck was meant to observe the cosmic background, background radiation, which is the radiation that floods the entire universe with an average energy of 2.5 Kelvin. And the purpose is to detect tiny fluctuations on that energy to provide the mapping. Once again, you can see all this information if you go online about these missions. So our first task here was to tailor and modify and qualify the operating system that went on the main computer. As with the previous satellite, with the Sentinel, there was, of course, the main computer, and then there was an array of other instruments. Some of them have software, some of them don't, but the main ones, they also have software. So the main payloads, payloads, by the way, is the term that we use to define the actual sensors or the actual equipments that justify the existence of the spacecraft. For a scientific spacecraft, the sensors that the payload are the sensors, the scientific sensors that do justify the existence. In this case, the payload, you can see here the payload. This is the main reflector of the infrared telescope. These guys are a little bit further away from, or were a bit further away because they are decommissioned now. They were a bit further away from Earth, so they were in a location called Lagrange 2. You can see here where is Lagrange 2. So Lagrange 2 is one of the 5 Lagrangian points that are equilibrium points in gravity. So Lagrange 1 should be here. So when you are facing the sun, so you have here Lagrange 1, you have Lagrange 2, then you have Lagrange 3, 4, and 5 to the sides. So Lagrange points is a point where the gravity of the combined gravity of two bodies makes a null point. So there is a null point between the sun and the Earth, a null point behind the Earth, and then there's some other null points to the sides. So you can put spacecraft there. They are not really staying. They are just rotating around some virtual nothing. And if you want to make observations of deep space, Lagrange 2 is a good point to make observations of deep space. You are in the shadow of the Earth, and it's nice to do observation of deep space. You are in a cool zone if you want to make continuous observations of the sun or continuous observations of the interaction between Earth and sun, then it's common to put the satellites in Lagrange 1. Like, for instance, the SOHO was at Lagrange 1. So Lagrange 1 is the opposite way of Lagrange 2. Lagrange 2 is already a bit far away, but still the communication is not, it does not have that much lag, because there was a mission, that it's something important when you do software for spacecraft, that if it's a deep space mission, or if it's a mission that goes very far away, of course, it's not just point and click. Of course, that all of us get a little bit bored or upset if you go to a web page and it takes more than a handful of seconds to load. But if your mission goes to Jupiter, for instance, it may take 20 minutes just to have the signal synchronized with deep space antenna. So you need to care about the autonomy of that mission. And but in Lagrange 2 is still more or less feasible. It's not big deal. In a low Earth orbit or even geostationary orbit, it's okay. There's a little bit of jet lag, but no one really notices it. The next mission I have here, and this is one of the coolest satellites ever built. It really looks out of science fiction because it's really cool. All the others are just a piece of very, very, very ugly. Actually, if you go back, this is a rooftop. It's not so bad. And the goldish aluminum foil, which seems to be a far more expensive version of common kitchen aluminum foil. Actually, it is aluminum foil with a layer of something that makes it expensive, which is Compton. And that's an incident. Here is this spacecraft, which is much prettier than all the others because it has this very nice arrow shape. This is called Goche. It's something that was developed for observing the Earth, these tiny differences on a gravitational force. So you know the gravitational force as a constant. It is not exactly as a constant because, of course, it depends on the amount of mass of a given body. And Earth has a given amount of mass, and so that is not completely uniform across the globe. So there are tiny fluctuations around the 10 to the power of, when you go to the 7th decimal place and below the 7th decimal place, there are some fluctuations on the gravitational force on the surface. So at those scales, the Earth is not really too much round, as we will see. Here what happens is that these people, those satellites are not that much, or there are not many satellites, or not as many satellites as other things, but there is also a bit of a reuse. So here we have had something which was very similar to the platform, the onboard computer, and the onboard software of the central computer was pretty much the same, or the same framework, I would say, as in Cryosat, the first one we saw. So it's also an ADA95 implementation, also no operating system. So pretty much the same. Of course, it was modified to cope with the specific needs, but there was some reuse. So the two satellites are not too much identical, and the number of satellites being built is not sufficiently high for having out-of-the-box frameworks, highly reusable, but some reuse is possible still. So here you have something reused from Sentinel. Reuse here means it is not reused from some general purpose library that exists, is that in the individual companies that work on space business for a while, they have their own reusable assets that they use over and over again. So in this case, the reuse of the software for the onboard computer, it was because it has been worked with the same set of companies that were executing Sentinel. So when I said that the Earth is round, okay, here it is not this real shape of the Earth, but if you take the differences that exist in gravitational force, and if you magnify those differences, this is more or less what you have. So you have the weakest point of gravity is around the Indian Ocean, around Sri Lanka, and then you have very strong points of gravity around Iceland, and you cannot see it from here, but the other side in the Pacific around Japan. The reason this picture is here as well is that you have the software running on the spacecraft. You have, of course, the software running on the main computer, which is responsible for controlling the spacecraft. And you have other software there, of course. And at a certain point, you have software and hardware that controls the acquisition of the science data. And this science data goes first into a mass memory, and goes to mass memory because the satellite has not always visibility down to Earth. So you need to store the data in a mass memory for those periods where the satellite has no visibility down to Earth, because, visibility down to Earth means no visibility to ground stations to do the downlink. So you need to, and during the eclipse periods, you need to store all the science that you have collected, and you put it in the mass memory. Then you dump down all the science data plus all the data from, plus all the auxiliary data, mainly the data from the attitude and orbit control system. Attitude and orbit control system is a controller that maintains the spacecraft in a steady state, always pointing, because you don't want the spacecraft to be shaking the same way you don't want your camera to be shaking when you take pictures, unless it is your explicit intention to make some funny effects with the camera shaking. So here you download all the raw data from the sensors, and you download as well all the auxiliary data from the AOCS subsystem, such that then on ground you have multiple chains of correlation to put this together. So for instance, you have the data from the science sensors, and the data from the AOCS subsystems will tell you which was the position and inclination and attitude of the spacecraft at a given point in time. So then you start to have the timestamp data, you have the inclinations, and then you start correlating everything. So on ground you have a chain of processing. I have never worked on the ground processors. I know that there are level 1, level 2, level 3, and I think the reason is that because all architectures need to have 3 layers, because 2 is too less and 4 is too much. So I think that's the same reason for the levels of processing in the ground chain. So that's what it does. So it dumps down everything, and you also use the information from the attitude and orbit control system such that you can correlate the images, such that you can know what was the inclination at a given point in time. See, this here is a very strange box. It looks like a Tupperware. It should be launched this year. It's called Lisa Pathfinder. Lisa is not the name of a girl. It is rather the name of a laser interferometer space antenna. People in space like to use these names because it's much more fancy for ice-breaking conversations at the pub. Laser interferometer space antenna seems something very scientific indeed. There was a very particular challenge here. I was not particularly involved in that challenge, but it's a hell of a challenge. Imagine that you have a computer that is not sufficiently performant to execute the software you want to execute, and you don't have the chance to replace the computer, neither to downgrade much your requirements. As you'll see, this will be a hell of a challenge. You cannot, and the problem was the attitude and orbit control of this spacecraft is very complex. And this very tiny CPU, this ERC32 at 20 megahertz, was not sufficiently powered to execute the algorithms as they were. And there was no opportunity to actually change the computer. So there was should be something funny to assist to, or probably something very funny to be part of, but only 2 years after completion, because I believe that during the resolution of the problem, it was not so funny for the teams, or at least not so funny for everyone. But there was one of the challenges was, and that's one of the challenges that you need to face when you do software of this kind. The software, and that's because we are always dealing with real-time software, and real-time software is about you need to do something on a very precise amount of time, or you have a very specific deadlines. It's not about being fast or about being slow. It's about doing things at a very defined point in time, and that's and not being able to do that is what we call it a schedulability problem. So you want to have real-time software. One of the things you need to do is a schedulability analysis. That's why some of real-time software and embedded software looks a bit so primitive, because if you make it a little bit more complex, your analysis will burn you out and you will not like it, because if you make things very complex and very dynamic with very fancy threading models, it will be a nightmare for you to demonstrate it works, and therefore you can either do that and spend the rest of your life trying to demonstrate it, or else you make it simple. And if you have little computational resources, and if you are forced to make things simple, you get surprised in knowing that the 20 megahertz ERC32 CPU is completely capable of controlling the satellite. So if you will have a computer a third of the performance of your current computer, and you should do exactly the same things you do now, you will realize that you will be able to do it, because once you have less resources, you become a little bit more imaginative on how to use them, because you cannot have more resources. Here what we have is a ground station. So when we have a communication of satellites, you need to have something to communicate with them. This particular one is in Kiruna, as a place in the middle of nowhere in northern Sweden. There's the ground stations and there's an iron mine. And there are some pubs for the guys that work on the mines to go there and have fights on the Saturdays. That's basically, I have been to Kiruna and I can recognize it. I have not seen the antenna because it's further away from the city, but I can can confirm the fact of the pubs. So here, there is communication with satellites. There's a protocol stack from the first level of the OSIL model up to the application level. There is an organization called CCSDS, which I think means Consultative Committee for Space Data Systems, and they define a set of protocols. At the topmost level, there is an application level protocol that we know as Packet Utilization Standard, and that defines the essential features and the packets of the communication and the features of the central software. Not fully, but some. So for instance, this POS standards tells you that service 1 is telecommand acceptance reports. Service 2 is device commanding. Service 3 is housekeeping. Housekeeping is about periodic packets that are continuously being monitored and continuously being reported for ground for you to know the health of the satellite. So one thing that makes the software of a satellite quite different from other software is that you can change a lot of parameters, really tiny variables. So for instance, in one of the missions that comes after, there's something like almost nearly 20,000 things you can change. And you have equally a huge amount of parameters that are continuously being monitored and reported back to ground, such that the ground control knows what is happening with the health of the satellite. This is the last mission I have been working for a long time. So this I have spent there about 4 years. It's called Sentinel-2. It's an Earth observation satellite. It's also a polar orbiter satellite, sun-synchronous. It's optical. It captures certain bandwidths with a very high resolution camera. Two of the bandwidths are in near infrared wavelengths. All the other bandwidths are in optical. And if everything goes according to plan, it should be launched in June. I think the last date announced was 22nd of June. So if you check out on ESA website, you should see the launch of Sentinel-2 in the 22nd of June, or maybe one day after or so, because sometimes there are last-minute delays on launches. It's very nice. Still in this platform, we still have these ERC32. Here we had already a little bit more of memory. No 2 megabytes, but 8 megabytes. That's a huge amount of memory. And from Cryosat to here, what changed was the autonomy of the spacecraft and the amount of configurability that you could do on the spacecraft. So this is much more configurable spacecraft. There are some funny things here on the spacecraft to resolve the problem of the not having continuous visibility down to Earth. There is a laser communication terminal there, and the purpose of that laser communication terminal is to engage with a geostationary satellite and do a frame relay over a laser communication, and then the geostationary satellite can drop out and send back to Earth the signal in K-band, because it's telecommunication satellites is usually K-band. It's very nice. If you can see some articles about the laser communication in space, it's something rather experimental, but it has been proven to use. It has a huge, tremendous bandwidth capacity, and this will provide low Earth orbit satellites with a more direct link towards the ground. This is something which follows on the same platform as the Sentinel-2 satellite. This one is called Solar Orbiter. I have participated in the proposal and a little bit further support to the team. So my colleagues are working on this still. This goes back to the sun, to observe the sun, not like SOHO, because SOHO was making equatorial observations of the sun starting from the vantage point of Lagrange 1. This goes continuously into several orbits around the sun, first in the system, Earth, Venus, then in the system, Earth, Mercury, and then it will continue in the inclination, and we try to make observations of the solar poles. So there was no observation of the solar poles ever before. So here, one of the challenges of this spacecraft is that the attitude and orbit control system, and not only the software, but the sensors and actuators, they need to be quite reliable, because the point is, if you see in the picture, the part that is facing to the sun, it is about 500 degrees C in temperature. And the part that is on the opposite side of the sun, it is minus 100 degrees C. So you have an amplitude of 600 degrees C in less than a meter. The flux, when you reach to the sun, the flux is so intense that the solar panels can never be fully facing the sun. They always need to be at an angle, because otherwise they will burn out. Of course, what protects the satellite is that it is impressive insulators, because not only Compton but others. There's fantastic insulators like aerogels and others that you can put an intense flame directly over them, and you put an ice cube on top, and nothing happens to the ice cube unless the normal heating up. So the platform here is similar to that of the Sentinel satellite. The challenge here is it is further away. You have to have autonomy. The satellite needs to work by itself for periods over 2 months or 3 months without contact, so it needs to be very autonomous. The other mission that is now starting, and we have some colleagues there, is Exomars Mission. This has a small rover that looks like Wall-E, and I don't know whether you remember, it really looks like Wall-E. It's a very nice rover. And this goes into Mars. The rover is a part of there's two twin missions. One carries the rover, and the second one carries the orbiter. So there will be two launches. So basically, the rover will do observations on the ground, send them back to the orbiter, and the orbiter will relay them back to Earth. Still, the rover will start to use new processors. The orbiter is still using this old school 20 megahertz system, which fortunately is no longer there. So what you see in the picture now is something called METOP. It is the first generation METOP satellites. I just used it because the second generation of METOP satellites is now being built. METOP satellites are satellites from the EUMETSAT, so they are weather satellites. So you know probably the Meteosat. It's quite common, the name Meteosat. Meteosat is the geostationary satellite. METOP is the solar synchronous satellite, so they complement each other. And this is a picture of METOP. What happens nice is that now they are doing the new METOP, this called METOP second generation, and now we have much better computers. So now we have Leon 2 computers. Leon 2 computers are Spark V8 implementations, and imagine what? They can go up to 100 megahertz. There are multi-core versions of them, and now we have some implementation with 512 megabytes of RAM. That's a complete jump. So finally, there's a jump to something funny. So now we start to have multi-core CPUs for space. Sometimes the multi-core functionality is not used, so the cores are just disabled. But the features are there. So it's the multi-core CPU is available. So you jump from Spark V7 to Spark V8, which is not a big jump. It's just the instruction set is pretty much the same. The Leon 2, which is an implementation of the Spark V8 instruction set, actually uses the AMBA bus from ARM. So it's very nice. So it's much more performant now. So there's much more place now to do exactly the same as before, but with much more code. That's what happens. So if you have much more space, your disk space increases. So you just put the random DLL generator from Microsoft, and it will make make you feel like you have exactly the same space as before. So I don't know whether it is much better to have much more computational power now than before, because it will be like in the theory of ideal gases. They always occupy all the space available. And but okay, it's better to have a nicer CPU, because the ERC32 was already pretty old. And I believe it's my end of my time. I appreciate you being here and really just coming. I'm sorry, I will make the presentation again all over to you. Thank you. But then you pay me a beer. Okay. Okay. Thank you very much for having me. And there's not much to copy from this presentation. The pictures are nice, but you can find them all on Google Images.
Nós estamos avançados no tempo. Não sei se não sei se tem questões, tanto para o primeiro orador, para o Cristiano, ou agora para o João. Se tiverem questões, temos ainda espaço para elas.
Bom dia, o meu nome é Gonçalo Lourenço. Eu tinha uma pergunta para o orador João Esteves. Por que eu uso a linguagem ADA?
English. So the question is about how to use, why to use Ada programming language. And the reason was Ada programming language was built to be type safety, to be actually very safe. So the good point about Ada is that it forces you to make some software that is far more safer, far less prone to bugs. So unless you really hit the language quite hard, it's very difficult to have things like buffer overruns or mixing up types, because that's the reason why it is so strong typed. And when I tell that if you never used Ada, your software will not be compiled during 2 or 3 weeks, that's really the case, because it's really not compiling, because it always claim type is incompatible. If you want to see a good justification about a good description about Ada or any other programming language, there is a a collection of websites with small variations on the subject. That is how to shoot yourself in the foot using several programming languages. And there's a good descriptions there for C. For C, either you shoot yourself in the foot and then you realize that you have used a cannon, not a pistol, because of a cast problem. And in Ada, you have, for instance, you try to shoot yourself in the foot, and what you do is you simultaneously and concurrently pull the trigger, load the gun, and point to the foot and shoot it. And what happens when you shoot it, it says, your foot is of a wrong type. And that's how it works in Ada. So that's why it is used. So the Ada has been promoted mainly, initially, as a defense, by the defense establishment, but it is used because people like it because of their safety properties.
Thank you.